the squeeze theorem. So let's say f is sandwiched between function h and k. So I have a graph. We have f right in the middle. We have k above f. We have h below f. So f is sandwiched between h and k. And then here is how we represent that using inequality. And h of h is less than or equal to f. F is less than or equal to k. So when you pick a point, k has the highest y, and then the next one is f, and then the next one is h. So k is greater than f, f is greater than h. And then the limit of h and k is equals to L when x approaches to c from either side. So as x approaches to c from the left or from the right, k and h, the limit is equals to L. All right, so that means the limit of h and k is easy to find. When x approaches to c, the limit is just equals to L, and then the limit of f of x equals to L. So what is the purpose of using the squeeze theorem? So for squeeze theorem, usually in the limit, one of the terms is hard to evaluate. I should not say one of the terms. I should say the entire limit is hard to evaluate. You cannot use any conjugate. You cannot do any algebra. You cannot rewrite the function to make the limit easy to evaluate. The limit is hard. So when you look at the limit, there is nothing that you can really do. Then you have to think about something else. Then you have to think about a function h and k, and then the limit of function h and k is easy to evaluate. As a result, since f is between them, so the limit of f is just equals to h and k. So do you see that in this picture, h, f, and h, k, and f, they join at the same point when x is equals to c. But when x approaches to c at f, the limit is hard to evaluate. All right, so we will be using k and h as assistants to help us evaluate the limit when x approaches to c for the function f. So two typical examples I can give you below is here. So we have limit as x approaches to infinity, 2 times sine of x over x plus 1. If you just plug in infinity, sine of x, you cannot determine that, and then for the on the bottom, you have an infinity. So what do we do in this case? So for a squeeze theorem, usually there is a sine square, cosine, or cosine square in the function. So for this one, you have to say that a sine of x is between -1 and 1. So think about the graph. So sine of x, I should put the y-axis in the middle. So for sine of x, you have this, right? So this is a 1 period to the right, and then a 1 period to the left. That is between 1 and -1. So sine is between -1 and 1. So look at this compound inequality. The next step is we will multiply each side by 2. So -1 times 2, that is -2, less than or equal to 2 times sine of x less than or equal to 2. Okay? So multiply each side by 2, and then we are going to divide each side by x plus 1. So we have -2 divided by x plus 1 less than or equal to 2 times sine of x divided by x plus 1 less than or equal to 2 divided by x plus 1. Okay, so this is my h, and then this is my k, and then this is my f in the middle. All right, so here is what we are going to do next. What happens as x approaches to infinity? As x approaches to infinity. So for these two limits, it's easy, right? As x approaches to infinity, you have a 0 in the denominator, right? Oh, sorry, you have an infinity in the denominator. So -2 divided by infinity is 0. 2 divided by infinity is equals to 0. So basically, the function that we are trying to evaluate, or the limit that we are trying to evaluate, is sandwiched between two zeros. Okay, so I start as x, and then I draw this inequality. Sine is between -1 and 1, and then I'm going to build on top of that, multiply each side by 2, divide each side by x plus 1, and then I evaluate those two limits. Because when you do this, you can do a simple evaluation without the sign. Okay, so since the limit that we are looking for is sandwiched between two zeros, then this is just equals to 0. then this is equals to 0. So as a result, this limit is equals to 0, and then we say this is by squeeze theorem. So by squeeze theorem. So if you change the sine of x to cosine of x, you will reach to the same conclusion, right? So if you change the sine of x to cosine of x, you can try that yourself, because cosine of x is also between 1 and -1. Now, in the next example, what happened when you square the sine? So when you square the sine, that changed the entire story, and students ask me this all the time. So for sine of x, the graph looks like that. So you have one period to the right, and then you have one period to the left. So what happened when you do a sine of square? So what happened when you square? This is between 1 and -1. When you square the sine, do you still get negatives? The answer is no. When you square the sine, you will get all positive. So that means you will the piece below the y-axis, they have to flip like this. It's no longer going down. This piece will just flip up like that. So this piece will just go up and then go up. We do not have any pieces below the x-axis because you square the sine. So there is no more negative. So this is how we start. I just write sine. Just start with sine. Sine of x is between 1 and -1. This is the same thing for cosine square. If you change the sign of sine to cosine, you will get the same conclusion. And then here is the trick. So when you square each side, this will be sine square of x between 1 square is 1, and then this one we will just write a 0. Now, the question that people ask me all the time is, they say, hey, the square of -1 is not 0. I know the square of -1 is not 0, but this is based on the picture between 0 and 1. Look at the picture. This inequality is based on the picture. Can you write this down in case you will ask me again? So that is based on the picture between 0 and 1. So now we build on top of that, divide each side by x minus 1. Divided by x minus 1. So do you see that the other two pieces are very easy to evaluate as x goes to infinity or -infinity? So this one is just a 0, right? Less than or equal to. This one is a 0 as well. So this limit is sandwiched between 0 to 0. So that is also equals to 0. Okay, so overall, the limit is equals to 0. So whatever that is, that equals to 0 by squeeze theorem. Alright, so that is the end of this video. I don't want to make the video too long, so I will introduce a couple more different types of example regarding squeeze theorem. Alright, so stay tuned. See you over there.